So what I want to do now is look at a couple of examples of how to use L'Hopital's rule when we're dealing with an indeterminate case of 0 over 0 or infinity over infinity. So I've got two examples here. I want to address this first one, 0 over 0. Now, remember, L'Hopital's rule deals with situations where we have cases like this. In other words, here's an example of 0 over 0. Notice that the limit on the top, if I take the limit of this top, okay, the limit as x goes to 0, okay, if I take the limit of this thing, cosine x plus 2x minus 1, that limit, if you plug in a 0 here, what you get is 0. And of course, if I take the limit of the bottom, the limit as x goes to 0 of 3x, well, of course, that's 0. So we have this situation where taking the limit of the top and putting it over the limit of the bottom does not tell us what the limit is. We just get 0 over 0. That limit could be a lot of different things. It could be 1, it could be 0. We just don't know. So it's an indeterminate case. Now, we're also, in this video, going to look at the indeterminate case of infinity over infinity. I have an example for that one. There are other indeterminate cases, though. There's 0 times infinity, 0 to the 0 power, infinity to the 0 power, 1 to the infinity, infinity minus infinity. And we'll look at those in future videos. But right now, let's see how we deal with this one. Okay, so we have determined that this is the indeterminate case. Okay, so we got 0 over 0. So here's what L'Hopital's rule tells us. We can take the limit of the derivative of the top over the derivative of the bottom. Okay, so I'm going to take the derivative of the top, and that is negative sine x plus 2, and I'm going to put it over the derivative of the bottom. Now, be careful here. We're not using the quotient rule and differentiating. So I'm not taking the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. No, it's the derivative of the top over the derivative of the bottom. So what L'Hopital's rule tells us is that this limit is equal to this one. Now, let's see if we can evaluate this limit. If I put a 0 in here for x, I get 0. Sine of 0 is 0. And then I just have a 2 over 3. So our limit is 2/3. Now, who would have thought that? I mean, looking at this thing, we got 0 over 0. We didn't know what the limit was, but as we work through it, we find, yeah, that limit is, in fact, 2/3. So that's an example of how we use L'Hopital's rule for the case of 0 over 0. Now let's look down here at a case where we have infinity over infinity. Notice I've got the limit as x goes to pi over 2 from the left, and I've got this function 4 tan x over 1 plus secant x on the bottom. Now remember that for tangent and secant, both of those have asymptotes at pi over 2. So here's the pertinent part of the graph for tangent. And notice it's going off to infinity here at pi over 2. And here's the pertinent part for secant. And notice it's going off to infinity over here at pi over 2. So we have this case where we have infinity over infinity. That's an indeterminate case. So we can use L'Hopital's rule. Now, if we don't have an indeterminate case, we shouldn't use L'Hopital's rule. But this is the indeterminate case. So let's see what we've got here. We've got the limit as x goes to pi over 2 from the left. Okay? Now, let's see here. The top, that's going to be 4 secant squared x. That's the derivative of tangent. Now, on the bottom, we've got 1. The derivative of 1 is 0. The derivative of secant is secant tan. Secant x tan x. So there's what we have. Now let's see what we can do. Now, first thing you notice that we can kind of simplify this. So let me move down here and give myself a little more room. I've got the limit as x goes to pi over 2 from the left. And notice that that secant, one of those secants will divide out. So I've just got secant x up top, and down on the bottom, I've got tan x. Now, we're still not ready to evaluate the limit. I need to simplify this a little bit because notice we've still got, infinity over infinity. And before we plunge in and start trying to differentiate again and use L'Hopital's rule again, we want to see if we can maybe simplify this. Now, remember, when we're simplifying trig functions, one of the tricks that we often use is that we convert everything to be in terms of sine and cosine. So, for example, up here I've got 4 over cosine x. That's what secant is. And down here I've got sine x over cosine x. That's what tangent is. And you'll notice here that the secants divide out. We could multiply the top and the bottom by, not the secants, but the cosines. We could multiply the top and the bottom by cosine, and we end up with this. We've got the limit as x goes to pi over 2 from the left of 4 over sine x. See? Because the cosines divide out. Now we're ready to evaluate this limit. Putting in a pi over 2, we get sine of pi over 2 is 1, so we get the limit to be 4. 4 over 1. So that's how we can use L'Hopital's rule. Now, I chose this trig function to illustrate this, the case of infinity over infinity. Notice that once we used L'Hopital's rule, we were still in the same situation, right? We still had, infinity over infinity. But what we did was we used our trig identities to simplify it. Okay, so we simplified it and then we plugged in. So that's what you have to be aware of when you're working with trig functions, because we could have used L'Hopital's rule again and said, okay, well, I still get infinity over infinity. Let me differentiate again. And we could be doing this all day. But using these trig identities helps us to get to where we want to be.